YouTube. Great. Live on YouTube and live whenever you click live on TikTok.
We'll do it live. I don't know where my phone is.
Last time I saw it was on, well, that was before the coffee break. And by that I mean when you went to school.
When I went to school?
And by that I mean when you went shopping for Valentine's.
Oh my God. Look at all these boards.
Beautiful.
Ignore that. Those are just me making my answer keys. Hello. All right. Welcome to my Thursday. Oh, I don't want to lose that. There we go. I need to like cover this with some cute paper, paint it or something.
Crafty and cute paper.
Crafty and cute paper, yeah.
You had some questions in your comments. Let's see. What can we start you out with?
Yeah.
First one. Where have you been all my life?
Aw. Very sweet. I've been here the whole time.
Let's see.
Well, what have I been doing this week with my students? I've been doing dilations and, there's some really cool stuff with geometry. So we've been getting into quadrilaterals, which are four-sided figures, right? Four-sided closed figures. And there's some really cool things, like especially with parallelograms. So with parallelograms, Casey, I can absolutely do a specific question. Well, let's see what your specific question is. I'll do my best.
I'm going to go bother the bastards.
Okay. Yeah, so Casey, just pop it in the chat there and I will get to it. So if we have a parallelogram, boop, 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 boop. Go like this, like this. So a parallelogram is when you have two sets of parallel lines. Now, so this includes, these are rhombuses or rhombi. Rhombuses, sure. Squares, rectangles. But like the thing that I was telling my students this year is, or not this year, but this week, with parallelograms, so a parallelogram has those two sets of parallel lines. So when you're looking at like the hierarchy of quadrilaterals, it's sort of like, it's almost like an improv class, right? Where you say like yes and. And so like a rectangle is a parallelogram. So it's got all the characteristics of a parallelogram, and it says yes, and all of my angles are 90 degrees. And then a square takes that and it says yes, and all of my side lengths are the same length. So it's like building on all of these characteristics. So all of these characteristics are the same thing. Okay, so like in a parallelogram, in any parallelogram, so this is a rhombus, this is a rectangle, you've got these two diagonals. Went a little bit off. Let's see, let's get this. Okay, so you've got these two diagonals. And what they actually do is they actually bisect each other, okay? So this and this, and then this, and this. They're bisectors. Okay. Now, if it's a rhombus, then those are perpendicular bisectors, right? So again, it's like yes and, right? All these things just kind of build on each other. So knowing these characteristics and things like that, we can answer some really interesting questions. Let's see. Yeah, Casey, no worries. If you just pop it into the chat, we will get you going, or we'll do our best. Let's see. Okay. Okay, so a couple of other things that are also true is that the opposite angles are congruent to each other. So like those two are congruent. And then these two are congruent. Okay. And if you think back to your geometry with transversals, right? If we think about, you've got two parallel lines and this one cuts across, right? So we've got this angle and this angle are technically their same side interior angles, which means that they are supplementary. Differential equations are we don't really get into differential equations here because those are getting more into like the end of pre-calc and calculus. So usually we kind of stop around like algebra 2 and trig. But if you pop your question in the chat, a lot of times there are lots of people in here who can also help you with those. So sometimes if you put your question in the chat, there are other people that'll join and they can help answer calculus questions or point you in the right direction. It's a great community we have here. It's awesome. But yeah, so if you guys have any specific questions, just put them in the chat, or any specific topics you want me to go over. I know people have tests and stuff. I don't know. We had a snow day today, so I'm still giving a quiz tomorrow, but yeah. Okay, so we can use this information about a parallelogram to find some different things. So if we've got a parallelogram like this, okay, not drawn to scale, okay, but it is a parallelogram, and we're going to kind of go with that. Oh, we can do similar figures for sure. Okay, so let's, ooh, that's actually a lot more complicated. Okay, so if I say that this angle is 5x minus 9 degrees, okay, and we'll mark these as being parallel. This is a parallelogram, but you know, when people come in and just see the diagram, sometimes they get fussy. So this is geometry, algebra 1, algebra 2, geometry. We'll say that this angle, so I'm going to say this angle here is 5x minus 9 degrees, and this angle here is 2x plus 30 degrees. So let's solve for x. Okay, so we've got 5x minus 9 degrees, and we've got 2x plus 30 degrees. So we know a few things about parallelograms, right? Yeah, we can totally do Pythagorean theorem. Okay, so let's see. Similar figures and Pythagorean theorem. Oh, I love the Pythagorean theorem. Okay, so I'll do Pythagorean theorem and similar figures after this. So with parallelograms, right, remember a couple of things, right? We've got our diagonals that are going to bisect each other. Then we also have, this is true, that the opposite angles are always congruent, right? 760 Fernando, you can absolutely be good at math. You're in the right place. Stick around. You can absolutely do math, okay? And you will be good at math, okay? All right, so if we know that these two angles are the same thing, then we can say that 2x plus 30 equals 5x minus 9, right? So we'll say 2x plus 30 equals 5x minus 9, okay? So whenever we're solving an equation, no matter what the equation looks like, we want to ultimately get it to where all of the variable is on one side and the numbers on the other. And then that's where we're going to have that equation. We're going to have that solution, right? So in order to make that happen, I want to get rid of the 2x on this side. So if I want to get rid of that 2x on that side, I'm just going to take away the 2x. Okay, so if I take away the 2x, that goes away. So now I just have 30 on this side. But I can't just take away 2x and say it's still the same thing. I've got to also take away 2x on this side, right? So if I have 5x's on this side and I take away 2x, then what I'm left with is 3x's, okay? Now nothing has changed with this minus 9. The equal sign is still there and the 30 is still there, right? So now I've got 30 equals 3x minus 9. There we go. Okay. So now if I want to get, I've got all of my x's are on this side. So now I need to get rid of that negative 9. So I could subtract negative 9, which like I would take away negative 9. But the way that I do that is actually by adding 9. So if I add 9 to this side, I have minus 9 plus 9. That becomes 0. But again, I can't just add 9 to one side. I've got to add it to both sides. That's a plus 9, not a minus 9. Okay, so now I've got 39 equals 3x. So if 39 is 3x's, the way I figure out how much 1x is I'm going to divide by 3. So 39 divided by 3, 39 divided by 3 is 13. Okay, so 13 is the value for x that proves that this is, or it's not necessarily that it proves that it's a parallelogram, but this is, so when we talk about these definitions of these shapes, right, and these characteristics of the shapes, it works both ways. So like in a parallelogram, these opposite angles are congruent. Now, what's also true is that if you have a four-sided figure and these two angles are congruent, it is a parallelogram. Well, if these two and these two, right? If the opposite angles are congruent, then it is a parallelogram, right? So talking about Pythagorean theorem, right? Pythagorean theorem is a squared plus b squared equals c squared for a right triangle, right? So if you've got three sides of a right triangle, you can use a squared plus b squared to equal c squared and find the missing side. But what's also true is that if those three sides fit into the Pythagorean theorem, it is a right triangle. So again, it kind of works both ways, right? So those equations and things do work both directions. Okay, so again, we know that if it's a parallelogram, then the opposite angles are always going to be congruent. So again, if I show that these two angles are congruent, then it is a parallelogram, right? So those things are always true. They work both ways. All right, so speaking of Pythagorean theorem, Pythagorean theorem and similar figures. So All right. So like I said, with the Pythagorean theorem, we've got two legs. We usually call them A and B, or B and A. It doesn't actually really matter, either one. Congruent is when you've got, it's like equal angles or side lengths. It's just a geometric term for the measurements being equal. So the measures are equal, the side lengths are congruent. It's kind of just a little bit of a distinction between those two things, right? Okay, so A, B, and C. I like to just say that these are the legs and then this is the hypotenuse, because the A and B or B and A, it doesn't matter which one is A, which one is B. The only thing that really matters is this, right? Is that C or this is the hypotenuse, right? That's the one, that's going to be the longest side always. So with Pythagorean theorem, what has been found is that if you square both of the legs and add them together, they are also going to equal the square of the third leg. Okay? So A squared plus B squared equals C squared. So again, if you're given three triangle lengths, like if we said like 3, 4, 5, right? I would see, okay, well 5 is the longest, so I'm going to see, is that C? I'm going to say 5 squared. And I'm going to see, does 3 squared plus 4 squared equal 5 squared? 9 plus 16 equals 25. And that is true, right? So these three side lengths are a right triangle. So it works both ways, right? So it works both ways. 3, 4, 5, if they fit into the Pythagorean theorem, it is a right triangle, right? And the other way, right? If it's a right triangle, the legs will, or the sides of the triangle will fit into the Pythagorean theorem. Okay. All right. Oh, yay. I'm glad you were at the Kansas City conference. Yay. That was fun. Those were really fun sessions that we had. Okay, so Pythagorean theorem, we usually use that for finding missing side lengths. But I mean, a little thing is that you can also use this for so many different things. You can use the Pythagorean theorem for so many things. So you can use it to find the distance between 2 points, right? Like distance formula is just Pythagorean theorem. That's all it is, right? You don't even have to memorize the distance formula. If you know how to do Pythagorean theorem, it works just as well, if not better. Right? Ah! Oh my God. Glad I was wearing my glasses. Almost took my eye out. My goodness. Okay. It's that snow day. I got a cabin fever. Why do we square root it? Tangent, cosine, sine more accurate. FTCE. FTCE 5 to 9. I'm not sure what that is. FTCE. Is that subject area for the teaching licensure? I definitely could help with that. Absolutely. Yeah, right? Like, they don't need to memorize the distance formula. If they just know the Pythagorean theorem, like, oh my gosh, it comes in handy all the time. And when you get into trig, right? Like, when you start with right triangle trig and you say, like, look, we can prove this, right? We can figure this out. Okay, so let's see. Unit circle. Oh my gosh, so many requests. So unit circle, mainly it's degrees to radians. Okay, and somebody asked earlier for similar figures, inverse functions, Venn diagrams. Holy smokes. Okay. For the Venn diagrams, are you looking at probability or is it just a Venn diagram in general? Okay. So with the Venn diagram, just pop a little bit more detail into the chat if you could. All right, so similar figures. I don't have A and B in the wrong spots because A and B are just the letters that we use for the legs. A and B, it doesn't matter which one's A, which one's B. So there's no right or wrong. It's really just the two legs, right? CC Spam, I welcome you every single time. Okay, so similar figures. So similar figures are not congruent figures, okay? So similar figures are where we've got two shapes, well, two figures that are the same shape but different sizes. Okay, these are from a dilation. Now this, I'm doing my best, right? We're going to say that they're similar. Okay, so I'm going to call this ABC and DEF. Okay, so the dilation, is when you're kind of expanding or contracting a figure. Right, so we're going out or we're going together. And it's like when you have an image in a Google Doc or something and if you grab just the side and just change that dimension, it's not going to look right, right? If you take the top and you do that, it's not going to look right, right? If you just change that dimension, it's not going to look right. But if you grab the corner and you change both of the dimensions by the same amount, it's gonna keep its same characteristics, right? Now, if you're just stealing an image from like Google Images or something, well, it's probably going to be pretty blurry. But with a figure like this, right, if you expand it and contract it, you've got all the same proportions, right? So the ratios between the sides are all the same. So these two figures are similar. They are not congruent, but they are similar. So I'm going to say that triangle ABC is similar, and the symbol for similar is just this one squiggle. Okay, is similar, oh wait, this should be triangle. ABC is similar to triangle DEF. Okay, so I've done a couple of things now, just by saying that they're similar. So especially in geometry, but in most math classes, like every single term is like a loaded term. Like saying that these things are similar, like it sounds very friendly, like, oh, they're just similar, like they're kind of close. But it means a lot more than that. It means that like these two angles are congruent. These two angles are congruent, and these two angles are congruent. And the relationship between this side length and this side length is the same as this side length to this side length. Okay, so that is what we're looking at. So the angles are congruent. So we have congruent angles, which is congruent is an equal sign with a little squiggle on top. So congruent angles and proportional sides. That is what similar means, is that these angles are all congruent. So when we look at this similarity statement, the order does matter. The reason they're in A, B, C, D, E, F is not because they're alphabetical. Okay? If I were to change this to be D, E, F, okay? This similarity statement is wrong now because angle A does not correspond with angle D, right? Angle A is here, angle D is up here. So I actually need to change this because the similarity statement is a lot more than just telling you which two triangles we're looking at, right? So angle A corresponds with angle F, so this would be F. Angle B and D, and angle C and E. Okay, so A matches up with F, B and D, C and E. Okay, so if I give you some of these measurements, right? So angle A is congruent to angle F, angle B is congruent to D, angle C is congruent to E. If I gave you some of the lengths, okay, like let's say that this side is 4. Okay. And this side is 10. And then let's say that this side is 7. Why not? Okay. Let's figure out what this side would be. So we've got 4 and 7, 10, and don't know. Oh, we got 17.5. Okay. Ooh, you just had a test on this today. Hopefully you did well. I feel like the consensus is 17.5. Let's see why it's 17.5, or if it's 17.5. I think it's 17.5, but I just made these numbers up, so I don't know. Let's find out together. Okay, so these are, you know, you're the second person tonight that's been asking for differential equations. So I don't do differential equations here, but I'm sure that there are some people in the chat that can help you with differential equations. Usually there's a lot of people that are in here that do a little more of the kind of advanced math, but I usually just go to like 74. I usually just go to like algebra 2, some pre-calc, but we're not quite to differential equations. Okay, so proportional sides. Okay. So the relationship between side AB and side AC is going to be the same ratio, is going to be the same relationship as the corresponding sides. Okay? So here we're going to have AB over AC is the same thing as the relationship between side FD and FE. Okay? I can get this relationship. Now I could set up this relationship as AB over FD equals AC over FE, as long as I've got it kind of consistent, right? So now I'm going to fill in what I know. So I know that AB is 4, right? So I'm going to do this. So 4 over AC, which is 7. And I've got FD is 10. And FE is my question mark. I'm just going to go ahead and call that X. Right? So solving a proportion, okay, there's a lot of different ways to solve a proportion. I like cross multiplying, okay, where you multiply across and those cross products are going to be equal to each other. But there are other ways that you can do it, right? You can do, there's lots of other ways. You can do like, what is it? 10 divided by 4 times 7, right? Okay, there's lots of different ways that you can do these, but I like to do the cross products, right? So I got 4 times x, which is 4x, equals 7 times 10, which is 70. Okay, and this is just something that is always going to be true, okay, is that these cross products will equal each other, okay? So now we can divide both sides by 4 to get that x by itself. So 70 divided by 4, let's see. So 70 divided by 4 is 17.5. 35 over 2 or 17.5. So x equals 17.5. Yay! Gold star, everybody. Oh my gosh, I was going completely off the board. I'm sorry. Teach me to look up a little bit every once in a while. Okay, so we've got, there we go. Right, so we set up the proportion with the side lengths. Okay, we filled in what we knew, and then we cross multiplied and solved that to get our product. So we've got 17.5. Okay, now what you can also do is you can do Like I said, you could do 10 divided by 4 times 7, right? That's called the scale factor. So the scale factor is what am I going to multiply by to get my other side lengths. So some of you may have noticed that 4 times 2.5 gives you 10. So 7 times 2.5 would give you x. Totally fine, right? That is absolutely a totally fine way to do that, right? That's finding that scale factor. Okay. Okay. All right. See ya, Cece. Okay, how do you find the mean of a line on distance formula? Triangle. What? How do you find the mean of a line? Do you mean midpoint? Okay. Let's do pivot columns and free variables. Oh, okay, midpoint. Yeah, we can find midpoint. Okay, so we did simfigs, similar figures. Okay, let's do Venn diagrams. And then, all right. So, all right, so a Venn diagram is a way to show how things are kind of arranged, okay? Now, I'm going to come at it from a probability lens. So, meaning, let's say, okay, hold on just a second. Oh, I don't think I have my dice. Dang it. I didn't bring all my dice in here. Okay, so let's say that we have a D20 dice, okay? A D20, you've got 1 through 20, right, on all those sides. So I'm rolling it, and I wonder, like, what are the odds, right? What's the probability of me getting, you know, an odd number? What's the probability of me getting a number that's greater than 6 or less than 5 or an even number greater than 17, right? Something like that, right? So we need to look at these. This is getting into that set theory, or set theory, which is where you're looking at what are my possible outcomes, right? And again, I'm just coming at this from a probability lens, but this can be applied in a lot of other ways too. So let's say that I'm going to say that, like, event A, so outcome A is, okay, so I'm rolling a D20. So you're going to roll a D20. And again, that's just a 20-sided die. Use them in D&D, all that great stuff. And this is my pitch for partnering with Dimension 20. So you roll a D20 and you want to know what your possible outcomes are, right? So now you've got, let's say event A is you want to know, you want to roll greater than 15. Okay. So you're going to roll greater than 15. Okay. But you're like, you know what? If I don't roll greater than a 15, I'm still okay if I get, like, you know, maybe roll an odd number. Maybe just roll an odd number, sure. Okay. So we've got these two possible outcomes. Okay. Now when I'm looking at these with a Venn diagram, okay, this is my whole experiment. Okay. This rectangle is all my possible outcomes. So this is everything that could possibly happen. So 1 through 20, right? This is my whole sample space. Okay. Now, I want to pay attention to if I roll greater than a 15, right? That's my first little grouping that I'm going to make, right? Is if I roll greater than a 15. Okay. So what's going to go in there? Let's see. We're going to have 16, 17, 18, 19, 20, right? Right. Universal set. Thank you. That's what I was looking at. That's the word I was looking for. Okay. And then event B, now rolling an odd number. Now there are odd numbers that are also greater than 15, right? So there is going to be some overlap, okay? So if I look at this Venn diagram, there's going to be some overlap in there, right? So event A is rolling greater than 15, and B would be rolling an odd number. So this little intersection here is going to be rolling a number that fits in both of these. So it's greater than 15 and an odd number. So that would be 17 and 19. 17, 19. That's so tiny. But those are the two numbers that fit into both of these categories, right? Now, we've got rolling an odd number. We've got 1, 3, 5, 7, 9, 11, 13, 15. Now, I'm not going to list 17 or 19 because they're already here in that overlap space, right? Greater than a 15, I've got 16, 17, 18, 19. Now, out here is going to be everything that's not in A or B, right? So anything that's not in A or B, that would be, let's see, 2, 4, 6, 8, 10, 12, and 14. I think that's it. Where's 20? Oh, 20 is in A, isn't it? My goodness. I forgot 20.
You got a question from YouTube whenever you're ready.
Oh, there's lots of questions. Yeah, so these would all be the complement, which is that they're neither A nor B, right? Okay. From here, you can do a lot of different things, right? So if you're looking for the sample, if you're looking for the sample space of A, right? The sample space for just A would be 16, 17, 18, 19, 20. All right, that's your sample space because that's everything that's just in this part, right? If you're looking for A and B, that's what that symbol means. That's an intersection. Oh my gosh, sorry. That's an intersection is A and B. So what are the numbers that fit in both A and B? 17 and 19, right? Those are the only two that fit into both of those. So 17 and 19 are both greater than 15 and an odd number. Okay. Okay. So we're just talking about Venn diagrams right now and sample space and all of that. Oh, a little 18s. Okay. So that's kind of what you're talking about with the Venn diagram and getting into the sample space. Okay. All right. Okay. Unit circle, degrees to radians. Okay. So I can't do a lot with the unit circle on here because it's hard to show with all of this. So I'll show you what I can show you. Okay. So we've got our circle. Oh, a pretty good circle. It's a little bit of an egg, but okay. So our unit circle is like this, right? So all the way around the unit circle, or all the way around any circle, right, is 360 degrees. So here it would be 0 degrees or like 360 degrees, right? That's in degrees. Now in radians, it is 2 pi. Okay, so radians is 2 pi, so degrees is 360. So if I just go to 180 degrees, well, how many pi would that be? It'll just be 1 pi, right? Half of 360, half of 2 pi is just 1 pi, right? Okay, so 90 degrees up here would be what? It would be half of a pi. So it's pi over 2. Okay, half of pi. So down here, let's see. So if we look at this as we've got 1 pi, and then we've got another half of a pi. So this is going to be 270 degrees, and this is 3 pi over 2. You know, it's kind of hard to type that into the chat, right? So that's going to be 3 pi over 2. So the conversion rate, so converting between radians and degrees, you use this relationship right here with the 180 and pi. So when we talk about like the unit rate, right? Like, and this is going back to like, you know, when you have like 60 minutes in 1 hour and you're trying to figure out how many hours is 30 minutes, right? And you use that sort of relationship to do that conversion between minutes and hours and all of that. It's the same idea, right? Unit rate conversions are unit rate conversions. They never really change. So right here, that 180 over pi, that is the rate that you're going to use, okay? So if we have something like the unit circle really is, that wasn't great. That was not a great 45-degree angle. Okay, so the unit circle, there we go, is based on increments of, I guess we would say, it's 30, 45, and 60. That's basically what they do. Right, so 30 degrees, 45 degrees, and 60 degrees. Okay, so this is 30 degrees, this is 45 degrees, and this is 60 degrees. Okay, it's all fractions of pi. That's all it is. Okay, so 30 degrees, or let's say 45 degrees, right? 45 degrees is half of 90. Right? So that means that in radians, it's got to also be half of pi over 2. So half of pi over 2 is pi over 4. Right? Okay. So we can use this logically, or we can also just convert it. We can say 45 degrees, okay, and I'm going to multiply it by pi over 180. Because I know that radians have pi in them. So I'm going to leave pi on the top so it goes in there. So I do 45 divided by 180, which gives me 1/4. 45 divided by 180 gives me 1/4, so that's pi over 4. Exactly. So it'd be 45 pi over 180, and then you simplify it, right? I like to just kind of like stick the pi in there like afterwards, right? Figure out what the fraction is and then just slap a pi on there. So you can use this if you know these 30 degrees, 45 degrees, and 60 degrees. If you know this first quadrant, you could do the whole unit circle. All it is it's just fractions of pi, and it's really just like 1/4. And then like if we have 30, right? 30 degrees is 1/3 of 90. So 1/3 of pi over 2 is pi over 6. Okay. So radians to degrees, if I had something like 4, well, let's do, not 3 pi over 2. Let's do 4 pi over 5. Okay, so 4 pi over 5, I would multiply that. Now remember, my unit rate is pi is 180, right? 180 in pi over 180. So in this case, I want to go to degrees. So I know degrees don't have pi in them. So pi is going to go on the bottom. The reason it's going to go on the bottom is so it cancels out. Pi over pi is just 1. And then what's going to go on the top is 180. So now I've got 180 times 4. So 180 times 4, which is 720. I'm going to divide that by 5, which is 144. So this is 144 degrees. Now, that's not on the unit circle, but you get it. You can still convert it, right? Okay. So really, I mean, the unit circle, again, if you just can puzzle your way through this first quadrant, you can figure them all out. And if you just know this pi over 180, you can, and do I want to get rid of the pi or am I adding the pi in, right? The coordinates for these angles. You mean like on the unit circle? Annalise? So if you know the special right triangles, yeah, that gets into like the, okay. All right, we're doing a deep dive on the unit circle, which is fine. I love it. Okay. So the unit circle is all of this. Okay. All right. I get it. You guys have a test tomorrow over it. Let's do it. Let's get into it. Okay. So the unit circle is a circle with a radius of 1. Okay. So that means that this distance here is 1. So that point is 1, 0. Okay. This length here, this distance here, again, it's from the center to the side of the circle. That is also 1. Okay. Now the coordinates for this point, though, are a little bit trickier. Okay. Now this is a third. Now, okay. So here's what I'm going to do. I'm going to. What am I going to do? Okay. I'm going to redraw this, but I'm just going to draw this coordinate, okay? Because again, you guys we can sort of sort out the rest of it if we just know the pattern that's in that first quadrant, okay? I offered my students extra credit if they memorize the unit circle. And a lot of them did it, which I was surprised. I was pleasantly surprised. It was exciting. Because usually you can at least access a unit circle, which is nice. Okay, so let's go with this. Okay, so we're just going to have the unit circle. And again, I'm just going to do the first quadrant, even though we know it keeps going through. Is that going to work? That's not great. Okay. Let's draw it out a little bit bigger. Oh, that's even worse. Oh no. I know, guys. It doesn't matter. It doesn't matter. It doesn't matter. But it does. I'm just going to start over. Stop it. I have a generalized anxiety disorder. Okay. Okay. Ooh, look at that. Okay. So again, this point here is 1, 0, right? This point up here is 0, 1. Because the radius of the unit circle is 1. It's 1 unit, right? It's the unit. Okay. So now we got, I thought I had a ruler in here. I do have a ruler in here. Okay. So we've got our 45 degrees here. So 45, 60, and 30. Okay. All right, so this is 30 degrees, right? And to figure out these coordinates, so the coordinates, well, the important thing is with the unit circle, right? It's standardizing everything. So this is a 30-degree angle. Okay. Now we know that this hypotenuse is 1. Okay. Because it's the radius of the unit circle is 1. Now if we think about a special right triangle, side, special right triangles, I've got 30 degrees here, I've got 60 degrees here. This side is A, this side is 2A, and this side is A times root 3. Okay. Hopefully, if you are doing trig, you have learned the special right triangles. If not, here it is. Okay. So when we look at the unit circle, exactly, it's just a 30, 60, 90 triangle. If this is 1, right, the hypotenuse is 1 because it's the unit circle, right? So that means that this, so 1 is 2A. So this side length is 1/2. Right? Because half of 1 is 1/2. So that means that the y coordinate of this is 1/2. Because that side of the triangle is 1/2. This side of the triangle is A times root 3. Well, 1/2 times root 3 is root 3 over 2. So that is my distance here because it's just a 30, 60, 90 triangle. So root 3 over 2. So those are the coordinates for that point. Okay, for that point. And again, you've got 30 degrees. And so then that would also be, that would be pi over 6. Okay. Now, somebody asked, like, how would you figure out the trig function for this, right, with the unit circle, right? So the radical 3, the root 3 came from this special right triangle. So the special right triangles are 30, 60, 90, and 45, 45, 90. It's these triangles all have the same relationship. Okay, so in a 30, 60, 90 triangle, this side is a length. The hypotenuse is twice that length, and then the other side is the length times root 3. If you're in 8th grade learning the special right triangles, that's great. I mean, it's great if you're learning all of this, but yeah, you're good. So then law of sines and law of cosines we're probably not going to get to. We're not probably going to have time to learn that. I'm teaching this to my 10th graders. You're fine. You're good. All right. So the special right triangles here, that is what these are all based on. Okay. That's what this whole unit circle is based on, is these special right triangles. So we've got this pi over 6. So somebody was asking, like, what would the trig ratio be, right, for like using the unit circle? So using the unit circle for the trig ratios would be sort of like if we take that one triangle out, right? So now we're looking at this to this to this, right? We know it's 30 degrees here. We know that this is 1/2. We know that this is root 3 over 2. And we know that this is 1. Okay? So we got this triangle. We got all of these from our unit circle. So whatever measurement you have, you use the coordinates from the points to set up your triangle, okay? So if I'm looking for like tangent of this, right? So tangent of 30 would be, so tangent is the opposite over the adjacent. 30 is our angle. The opposite side is 1/2, and the adjacent is √3/2. So that would be 1/2 over, oh, I'm going to have to write this over here. So we're trying to figure out tangent of 30. So that's going to be 1/2 over √3/2. Okay. And when we're dividing, pancake mix, we're dividing fractions. Okay, so we're gonna like flip and multiply by the reciprocal, right? So we've got 1/2 times 2 over √3. Okay. The 2's cancel out, so we're left with 1 over √3. Now this is a little controversial because I am fine with leaving this here. The radical in the denominator, it's sort of an obsolete thing that people say, like, you can't leave the radical in the denominator, but I'm okay with it. But most teachers are not. So I'll show you how to rationalize it. So to get rid of the √3 in the denominator, so 1 over √3, what we would do is to get rid of that √3, okay, I'm going to multiply by √3 over √3, because that's just a version of 1 that's going to help me get rid of this √3. Okay, yeah, it's kind of like squaring everything, right? But I can't just square everything and get rid of it. So what I'm doing is I'm just multiplying. I'm sort of like being a little sneaky and multiplying by a version of 1 that's going to help me out. So I'm multiplying by this version of 1, because when I multiply this, I've got √3 times √3. Well, that gives me just 3 on the bottom. And then 1 times √3, it's going to give me a √3 on the top. So √3 over 3 is the same thing as 1 over √3. Now, this is my favorite like little calculator shortcut. If you are in this process of simplifying radicals, or you're, well, simplifying the, like rationalizing these denominators, or simplifying the radical or something like that, you would, you could actually double check to see if it's the same thing by just typing both of these into your calculator. And you're going to get a big, ugly, gross decimal. But if it's the same big, ugly, gross decimal, then you got it right. It's a simplified version, right? It is the same thing. They are equivalent. So that's good. So yeah, so this would be the same thing as √9, which is 3, right? Yeah. Okay. Ooh, 8:54. Okay, so hopefully that is helpful for figuring out. Somebody asked about the biggest advice for the math ACT or SAT. The biggest advice that I can give you is make sure you're comfortable with using formulas. Not necessarily knowing, like memorizing formulas, because they give you a whole formula sheet, but understand, they even give you like what the special right triangles are. It's pretty nice. But being able to manipulate formulas and knowing when to use them. So like volume, surface area, all of that. So being comfortable enough to know when you need a formula, but also other times, like when you don't really need the formula, you can just logic through it. Yeah.
There's a YouTuber that asks for domain and sets. Do you have time for that? Or
Domain and set, the domain of a set?
can you do domain and range in a set notation?
Oh, yeah. Yes. Okay, so we'll talk about domain and range because I know I've seen that a couple of times. The rule of rotation for 90 degrees. Oh, do you mean for like the counterclockwise and clockwise? Rule of rotation. Yeah. Okay, so domain and range. So domain is all the possible x values in an equation or in a function. Range is all the possible y values, okay? So when you've got an equation, okay, I'm gonna do, let's do this. We're just gonna look at like kind of like a limited equation, okay? So I'm just gonna look at this. Okay, so they asked for it in set notation, right? Okay. So right here, we've got this line. Okay. So this here, this is my domain. These are all my possible x values. Okay, that is my domain. My range is here. It's all my y values. Okay. Now, depending on the equation that you're doing, right? Depending on if you're doing like polynomials or quadratics and things like that, sometimes your domain and your range are all real numbers, right? If you've got a whole line that's going on forever and ever, your domain is, it's going to pass through every single x value there is. So it would be all real numbers. It's going to pass through every single y value. So it's all real numbers. Okay. So with this though, so my domain, I don't know if you guys can see this, but it starts at 2 and it goes to 2, 3, 4, 5, 6, 7, 8, 9. Okay. So to write this in set notation, well, so your domain, so set notation is you use a curly brace and then you say like x, and then it would be a colon, or no, actually it's a line, sorry. So x such that, that long line is such that, 2 is less than or equal to x, which is less than or equal to 9. So if you've got this set notation here, right, if we do this, we've got this range of values. Now, if you are just beginning domain and range, okay, if you've just got like, I've got to do the domain and range of these 5 points, okay, set notation would be just listing out those x's. So here I would say x with the bar, and then I would say like 2, 3, 4, 5. Okay, but in this case, I'm doing a line, so there is a range of values here. So my range would be the same sort of idea, right? I would use the same kind of notation. So my range, I do my curly braces, and for, well, it should probably say f of x, but I'm just going to say y right now, okay? Because f of x is like with a function, but we're just talking about range. So my range is going to go from 2, 3, 4 to 5. So y such that 2 is less than or equal to y, which is less than or equal to 5. Okay, so that's that set notation is with those curly braces like that. Okay. All right, guys. I know I didn't get to a lot of your questions, but if you leave me a comment, shoot me an email, join our Patreon. Oh my gosh, I love long division. We can do it next time. So if you guys want it, like, check out our Patreon. We did just start some new Patreon only subscription things and stuff like that. So check it out. And Oh, I got the little puzzle thing. That's okay. That's okay. Sorry, I got some little things going on. So check it out. Go join us. Go follow us everywhere else. Wherever you're watching this. Awesome. Yeah, keep an eye out and keep mathing. Have a good night. Let's see. Oh, it's not letting me do anything.